Hi, my name is Aggarwal, and this is my slideshow for Lab 3. In this lab, we talked about how to examine different batteries, capacitors, and resistors and how they behave in a circuit. We want to be able to predict the outcomes of having different resistors and capacitors in parallel, and we gathered different experimental data to test our hypotheses. In our results, we found that the sum of the voltage across the circuit will always equal 0, and we see that increasing the resistance of an RC circuit increases the time it takes for the capacitor to charge or discharge, and vice versa. So in this lab, we mainly use three main ideas. We have Kirchhoff's voltage law, we have the node law, and we have Ohm's law, since all of the resistors we used were ohmic. And so this is a picture of our setup. We had two different ammeters, and these are what they measured for the currents, and we found that the current from calculation is 0.02 amperes. And then we tested putting resistors in series, and the voltmeter had to be connected in parallel. And so the change in voltage across the 100 ohm resistor was about negative 1.9 volts, and the voltage change across the 47 ohm resistor was negative 0.9 volts. And so the sum of the change in voltage was about negative 2.85 volts, which we rounded to about negative 3. And so this is the graph that we made for part 1 of the lab, where you can see what we were measuring as the voltage change across each of the resistors. And at the end, you can see the voltage change goes back to 0. So then we had to calculate the resistance, and we wanted to see if it lined up with what we were told was the resistance of each resistor. And so the first resistor that we were told was 100 ohms, we calculated it out to be about 105.27 ohms, so not too off. And then the same thing with resistor 2, we were only off by about 2 ohms. And then we calculated that the wires had a resistance of about 10.87 ohms, and the ammeter had a resistance of 4.84 ohms. And then in part 2, we charged and discharged a capacitor, and this was our setup. The light bulb itself had a resistance of 10 ohms, and the capacitor had a 1 farad capacitance, and the battery we had still was 3 volts. And this is we timed how long it took to charge and discharge the capacitor, and so we were able to create this graph from that data. And same thing here. So then we get to our what if questions, where what if we charge the capacitor with no resistor in the circuit? Then in the ideal model, or in the idyllic world, we would have a capacitor that reaches full charge immediately, and the time constant would go down. The time constant tau would go down to 0, meaning an infinitely fast charging rate. And then our ideal model to predict the capacitor to full charge, once again, it would be instantaneous. And then this just would not really be possible in real life. It's not possible to charge the capacitor instantaneously. And what we measured is different from the predictive time. So because real-world circuits have just some resistance from the wires as we calculated in the battery terminals or the ammeter or the voltmeter that we had connected, that's why our measured time is a little bit different than the predicted one. And that's it. Thank you.